Welcome everyone to the beginning of Unit 8, What are integrals? And today we're going to look at Riemann sum and limit of the limit notation. So the idea of integrals is the area under the curve. So when you're finding the integral between two x values, you're finding the area under the curve. And so what does that mean? How could we find this area under the curve from y equals x squared from 0 to 1? Make sure you realize that's 1. And Riemann said, well, what happens if we can split up the area underneath the curve into little tiny rectangles? Well, in this case, we're going to break them up into 4 different strips at x equals 1/4, at x equals 1/2, 3/4, and 1. And we're going to split them up into triangles. This is going to be triangle S1, you can't really see that, S2, S3, and S4. And so, in this case, just this case, we're going to look at the right edge being the end value of that triangle. So we're going to look at this triangle there, there, and here. And so those are the triangles that we are going to look at if you want to look at it in terms of area. And then a very, very tiny one there. And those would all be filled in. I tried to keep them separate so that you could see that. But we've got to find the area. And yes, as you can see here, this is an overestimation. Right? We're going over it. But at least it will give us some idea. So we can say that the area under the curve equals S1 plus S2 plus S3 plus S4, where those are the areas of the triangles, or of the rectangles, excuse me. The area of any rectangle equals length times width, and so in this case, or base times height, or however you want to look at it. The bases are always the same. The bases are the distance here, so we're going to do 1/4 times the height. Now, how do you find the height? Well, the height is the right edge value on that curve. So in this case, to find the first height, you are going to look at y equals 1/4 squared, which we know is 1/16. So we can put 1/16 in here. Plus, what happens at 1/2? Well, that's going to be 1/4. And then, what about at 3/4? Well, that's 9/16. And then 1 is just 1. And then you would add all those up. And this will clearly give you, when you do the math, 15 over 32, or approximately 0.46875. And so what do we know? We know that the area under the curve is less than 15/32. So then, what could we do on the other way? Well, we could look at it from the left endpoints, being the left endpoints here, there, there, and there. And we could make our rectangles. I know they're not perfect. Again, fill them in. And yes, I cannot fill all those in. And you would get the same thing. So I'm going to pause it so you can write down your own area for area under the curve for this using the left endpoint. And hopefully you got 7 over 32, which is approximately 0.21875. Again, why did I write it like this? Well, this is the height. 0 squared is, we know that value right there, and 1/4 squared is the value right there. I could write it like that. You can see how I wrote it above. But these are just the heights. It is not always squared. People mess that up. I'm squaring it because the function is y equals x squared that we're looking at. It is not because I'm just squaring it for everyone. If it was x cubed, they would be cubed. If it was 1/2 x, I would just be multiplying by 1/2. So the conclusion that we can make is that the area is between 7/32 and 15/32. So another question is, how can we get a more accurate area using the rectangle method? Well, we could do midpoint, where it was right in the center, so you have half going over and half going under. could draw that better. So you see how it's partially there and partially over. That's another way to do it. Or there's the trapezoidal method, which if we look at it and we had this curve here to here, the trapezoid is a straight line going down, so you would have less area, and we'll look at that later on in a problem. But the area of a trapezoid, just so you have it, equals the height times base 1 plus base 2 all over 2. Another way they can write that is 1/2 h times b1 plus b2. And so here's a question that does not involve an actual function. It's just going to give you some endpoints here. So the function f is continuous, must be, so we can use Riemann sum, on the closed interval 2 to 14, and it has some values. This is important to know. This gives you the sub-intervals. It's telling you what we're going to use. So what I would like you to do is just draw a quick sketch of this graph with the rectangles. Pause the video and do that now. So you should have these three triangles. Notice that it said the right Riemann sum, and therefore that is why when I went at 5, this was our point right there, and that's why I'm going over. And at 10, that's my point, so that's why I'm going. I'm using the right endpoint to tell me how to draw the rectangles, not the left. If it had been the left, I would have been, I believe, down here. So another way to do that is right. Let's erase that. Right endpoints. I write out the intervals, and then I underline which ones I'm looking at. So if I'm using the right Riemann sum here, what I'm going to do is write out the three intervals. I'm then going to find the distance in between each of those intervals. So the right Riemann sum equals 3 parentheses plus 5 parentheses plus 4 parentheses. So I did the width of each of those, 5 minus 2, 10 minus 5, 14 minus 10. And then I look at what the right is. 5 is 28, so that's my height. 10 is 34, that's my height. 14 is 30, that's my height. And that will give me an answer of 374. And you can do the math for that. And that's all it is. The key is right. You're using the right ones. If it said left, you would have used 12, 28, and 34. Find the distance between them, the width of it, and then the height using the which endpoints, and there it is. Let's look at the next one. The next one said we're going to look at 4 equal subintervals of 0 to 2, so I already have them written out right here. And it said that we are going to have a trapezoidal, wrote out the equation, and the approximation. You do not need to draw it. So I'm not going to draw it. What I'm actually going to do is have you guys try to do this. But the one idea here is that the base is that we know that the base is the width and the height are these two. So I'm going to have you go 1/2. That's the 1/2 here. Base, which is 1/2, times B1, 3, B2, 3. And that's the area of the first trapezoid. The heights are the y values. So for this one, we're going to have 1/2 times 1/2 again, times 3 plus 5. And you guys finish the other two. And then get the answer and then check back in. And hopefully you got the answer of 12, and I showed a little more steps there. So once you feel good with Riemann sum, go back if you need to re-listen or re-look at some problems, and then we're going to go on to limit notation. One of the things I wanted you to see here is what the Riemann was thinking when he had the idea of finding area using rectangles. Now, we all know that looking at what is on the screen, thank you to Khan Academy and GeoGebra, that you can see that the rectangles get smaller in length, and as they get smaller in width, you get a more exact, precise definition of the area under the curve. You see how very little, the rectangle's width gets extremely small. A little area is actually above or below the curve. It's actually right on the curve. And if the width becomes so tiny that it's basically one-dimensional line, that you add all those lines up, you're going to get the exact value. And that's what we're going to look at here with the notation of Riemann sum. But this is what Riemann was thinking of how to find the area under the curve using infinitesimally small widths of for the rectangle. So looking at how to write this calculating area with Riemann sum using the summation symbol, what we are going to look at is calculating the width of one rectangle. You then have to find the height of the rectangle, and then you have to find the limit as the number of rectangles goes to infinity, which if there's infinity, that means they're so small, infinitesimally small, that you're going to get almost the exact area. So we've got to look at this. How do we do that? Well, we're going to calculate the width of one rectangle. The width of one rectangle, we can say, is the two boundaries, okay, b being the bigger number, so b minus a, divided by n. And why n? Because n is the number of rectangles, and we want n to be going to infinity. And so that's going to be, if we had the area, for example, from 0 to 1 of here, and we wanted 4 rectangles, we know, like we did in the beginning of the notes, it would be 1 minus 0 divided by 4. We have 4 rectangles of 1/4 length. Each rectangle is 1/4. So that's what we're doing, is calculating the width of one rectangle. Notice with identifying the boundaries of the interval, that's all that's saying is if we're looking at n, okay, that we're starting at the starting value and then we're adding whatever the change in x may be. So we could be going from 0, right here, the change in x, 0 to 1/4 would give us the first one, then 1/2, then 3/4, and then 1. So that's what this is talking about, this change in x, which was right here. We're going to write the sums of n terms beginning at k equals 1 all the way to k equals n. This right here is going to give you the height. This is going to give us the width. We talked about that width there. This is going to give us the height. The height being this a plus k times the change in x. And this is going to tell us how much more we moved over so that we can figure out that height. This is again how much we moved over from the starting of 0, moved over so we could get these height values. Then we're going to put it all together and add all those triangles up that we talked about. And again, look at where n's going to infinity because we want it to be an infinite amount of rectangles. I know that may not be the perfect way to explain that and that you may be confused. You are more than welcome. Khan Academy does a great job of discussing this with videos, and look up limit notation of a definite of Riemann sum, and there's some really good videos out there that you can watch. So, maybe a little confusing, bear with me. We've got 2 minutes to go over this. We got change in x. Change in x are the intervals pi over 2 minus 0 divided by n. That's going to give us pi over 2 divided by n, which is going to be pi over 2n. We are then going to find the boundaries, and we're going to find at the height. But we're going to look at a plus delta x. So a plus delta x. And that's going to equal a, 0, plus pi over 2n, which is just equal to pi over 2n. And now we're going to write it right to that point. We're going to go right to that point here. So we're going to go limit as n approaches infinity of delta x pi over 2n multiplied by f of, well, f of is a cosine function, so cosine of what a plus delta x was, so k, the k is out here, so k pi over 2n. That's it. So that is limit notation of Riemann sum. We're going to pause the video. You guys are going to go to part 2 of the video now, and we'll finish this worksheet up.